Hello and welcome to another Eigenverse tutorial. This series is called Unreal vs. Impossible, where I take things that you cannot do in Unreal and proceed to do them in Unreal. So for this episode, let's start by taking a look at this quantum simulation. As you can see, we have these colored lumps everywhere representing the wave function of particles. They're very smooth, they interact with each other interestingly, and they are all on this one plane. Now, for those of you who don't know, the wave function of a particle represents the space of possible locations in which you might find a particle. As these wave functions move around, the locations where the particle may be found move as well. But what causes the wave function to move around? Well, that's easy enough. If you look under the hood, you will find a bunch of tiny Makos running around, pushing up the quantum field above them. This, of course, forms the basis of quantum mechanics. So as you can see, the elevation and the color of the plane is linked to the location of each of the Makos. Now this might seem like an easy enough effect to attain. After all you need to do is link the material of that one plane to all the different Makos. However, it turns out that this is incredibly difficult, or at least very unintuitive, in Unreal Engine. This is because there's no real built-in tools for one material to access multiple objects. However, in this tutorial, we are going to find a way in which to pass an array from a logical blueprint into a material shader. You can consider this a very light introduction to incredibly advanced graphics programming, as we will be utilizing HLSL and everything that Unreal has to offer in order to attain this effect. Well, to get started, let's right-click here and create a new folder and call this Material Array Test. Let's double-click on that, right-click, create a new material, and call this Material... let's call this Array Test Mat. Let's now double-click on that, and now we are in the material definition in Unreal now, or the material blueprint, as it were. And if you're making a game, you're making a lot of these. What am I talking about with arrays? Well, the two things you'll probably do the most in here is hold S and click, which creates a scalar parameter, and hold V and click, which creates a vector parameter. Now, a scalar parameter is one value, for instance, 42.8. And this one value could be anything. You could, for instance, plug this right into the emissive right now, and this value will be the value of the brightness. This vector parameter, on the other hand, is 4 values, which are labeled here as red, green, blue, and alpha, although they could be anything. But for instance, if we wanted something that was really blue and just a little bit red, we'd get this color, which is really blue and just a little bit red. And we could plug this into the base color, and then we would have our object be that color. But what if I wanted more than 4 values? What if I wanted, say, 48 packages of 4 colors? Well, I could click and create 48 different vector parameters, but that would get old really fast. And then what would happen when I try to add the 49th? Obviously, this isn't going to work. We're going to need something else. But why would I want to do this in the first place? Well, one thing you might have considered is making a minimap for your game. Like, let's say you have a plane somewhere in the corner of your screen, and you want this plane to light up based on the location of, say, enemies that are scattered all around the screen. And as an enemy moves, you want the minimap to update in real time, showing that motion. But you don't want to create a bunch of objects and scatter it all over your minimap. You just want to do it all in the material. Doesn't sound like a tall order, but turns out there's no real way to do it in here. Or is there? Turns out there is one data type that can be easily passed between blueprints and materials that is actually a very large array of 4 vectors. And that is, you might have guessed it, the texture. Let's create a texture object parameter. Now, you might think of a texture as a picture, but I want you to suspend that mode of thinking for now and instead think of it as a large array of 4 vectors, each pixel being an element in that array, and the pixel's color being the vector. So how are we going to control this using logic? Well, let's minimize this and create our logic thing, which is a blueprint class. And we're going to base it on the actor class and call this array test BP. And then right-click again, go to materials and textures, and now we're going to create the object that interfaces between the material and the logic, and that is the canvas render target, and call this array test canvas. Now let's double click on the blueprint and see if we can mess with the canvas. Go to the event graph, and now we're going to drop down some nodes. Now, already I'm talking about controlling the location of enemies using pictures, and nothing here really makes any intuitive sense. That is the nature of this beast. This makes no intuitive sense whatsoever. I have no clue how I figured it out, but we're just going to go with the flow. Right-click and create Begin Draw Canvas to render target, and then right-click and create End Draw Canvas to render target. You just do this every time you draw a canvas to a render target, which is apparently what we're doing here. Now connect this here, and connect the context to the context, and we're more or less ready to go here. So first we're going to draw from the canvas and say draw texture. Now, I believe that draw texture is usually used to draw some sort of picture onto the render target. We're not going to use it that way because, like everything else in this video, this is a hack. What we're going to draw is one color to one pixel on the render target. So first let's type 1, 1, which says that it's going to be 1 pixel by 1 pixel. And now we can choose whatever color we like. Let's create a glowing red, just to prove a point here. And let's say its alpha is 1. Now let's choose a position for it. Let's say 2 along the X and 5 along the Y. Compile and save. And now we'll need to select the render target to use, so click on this arrow, select Array Test Canvas, and now connect Begin Play to the Begin Draw to Draw Texture to End Draw, compile and save, minimize, and now let's see if our logic does anything. Drag your logic into the level so it'll run when we hit play, and hit play. Alright, now hit stop. Now let's check into our canvas and see if anything happened. As you can see, we are drawing a little dot in there. You might need to uncheck alpha if that's checked. Sometimes it doesn't, you can't quite see it unless that's checked. But either way, now it is drawing something, and we have way too many elements in this array, because this is going to be 256 by 256, and I won't need that. Perhaps you do for your project, but I don't. So I'm going to set it to 16 by 16, save that. Now let's hit play again, and then stop. And now let's check in here, and that's a little easier to work with for now. So we're drawing a pixel in there, although it's not really drawing a pixel, it's drawing some sort of amorphous quantum lump in there. So let's see if we can fix that. Also, you might notice another problem here. If instead we drew it on the screen position of 0, 5, and then run that, well, first of all, it didn't erase the previous one that I had drawn. And secondly, this new one I created is looping around from the left side to the right side. There's some sort of toroidal topology going on here, aka asteroids effect. So let's fix that. First of all, let's erase the first one every time we draw a new one. And that's easy to do with the clear render target 2D function. So we'll throw one of those in there, and we'll tell it to clear to 0 on alpha. So to totally annihilate it. And let's make sure that it's this one we're using. We are clearing the array test canvas. So now we can run that. And now you'll see that the previous one was erased. Now only the new one is being drawn on begin play. The rest is deleted. Now let's take care of the wrapping. That's easy to do with here in the texture group. It's set to render target, but let's instead say 2D pixels unfiltered. I'm pretty sure this is the simplest type of texture. It's saved there, run it, and now you see we have just 1 pixel created. So okay, now we can render an arbitrary value to an arbitrary location on this render target. But now we can use arrays. Let's see how to do that. Go into the array texture blueprint, And let's create an array of vectors. So create a new variable, call this vector array, and make it a vector and make it an array. So now we have a vector array to work with. Let's just go ahead and set it for now. Or better yet, let's just set the vector array right now to an arbitrary vector. Let's drag out from here and create make array. And let's create a few of them. Let's say we had 5 of them. And let's say these are position values, somewhere in world space. So let's say there's one at -100 and 0 everything else, 100, 100 in Z, 100 in Y, and -100 in Y. Let's say this is -100 up here, yeah. So this should create a sort of plus shape. Now let's make sure this is connected somewhere in the logic. And now let's actually say for each run this and then set its render color equal to this vector. You can convert a 3 vector into a color vector, even though technically the color vector is a 4 vector. This will still work. We're also going to need to render these to different positions so that we can see them all. Let's, for now, say that we will render it to... Let's drag out from screen position and make a vector 2D. And let's say that the x value equals the index. And now let's disconnect this and connect it here and complete it. Things are getting a little messy, but we'll fix that later. Compile and save, and hit play. And then hit stop. Now let's see what happened. Indeed, now we are drawing multiple colors to multiple locations on the texture. Okay, so I applied this material to this grid. Now let's open up the material and start from scratch here and make this do what we want it to do. So what do we want it to do? Well, if we look at the render target here, I have these pixels here that are storing a variety of values. And I want those values to be the locations of, let's call them particles. Now, I want there to be glowiness around these particles, positions. So let's say there's one here. I want to, for each pixel around it, I want to loop through all of these particles and see how close it is to each of them, and then add that to its brightness. So hopefully this will become clear by the time I'm done with it. So let's go into the material here, and let's first create a texture object parameter. And just call this texture object parameter. And let's read into it the array test canvas. And now I could just sample this and drop it into the base color, and then you'd see the pixels light up there. But that doesn't read them as particles. In order to do that, we're going to need to write some code. So right-click and drop a custom node. And in the custom node, you can write custom HLSL code. Now, HLSL is probably the worst documented computer language in all of history, but if you happen to know it somehow, then you can do pretty much anything in Unreal or any other real-time rendering engine. So the first thing I like to do is set up the inputs and the outputs. Let's set the input to just simply be called input text. And then I'm going to run this into the base or the emissive color. So let's just mask out our output and make sure it's a float 3 with a component mask on RG and B. And let's actually take it into the emissive color. And let's actually output a float 4. This will be an RGB and an alpha value that we can use for whatever we wish. So first, delete that. And incidentally, to add a new line, you hold Shift-Enter if you're unused to working with this custom node. So what is it that we want to do in here? Well, ultimately we'll be outputting some sort of brightness value. So let's create a float brightness and initialize that to 0.0. Sometimes it's good to specify that extra 0.0 just so HLSL knows that you're working with a float and not an int. Now we can begin our loop. So first we'll create a for loop. For int I equals 0. Well, I is less than 16. I plus plus. So why is 16? This will work for any 16 value array. Now, I said that the appeal of this technique is that it can scale to an arbitrary length, and it can. However, for now, let's just keep it simple and just go across one row of this texture, which is 16 values. We'll learn how to extend it later, perhaps in another video. So, in the loop body, we need to read from each texel of the render target we created. That will be the particle's location. So for instance, this red particle will be far over in the x value, whereas the blue one will be higher up in the z value. Now, how are we going to fish that color out of that texture? If you've worked with HLSL before, you might think to use some sort of sample node, but it turns out that the thing we need to use now is called load. So let's say part position, let's call that a float 3, is equal to input text, which is the input variable we created, dot load. So load is a method of the input text object. And we are going to load. What are we going to load? Okay, so load takes two arguments, an integer 3 and an integer. Why the heck is that? Well, hopefully that'll make some sense once I do it. Probably not, but here I go anyway. Int 3 load location equals int 3 of I00 semicolon. And then we're going to load from the load location, comma 0. So what do all those arguments mean? Okay, so the load location here, the first value specifies the x value, the second value specifies the y, and the third specifies the minimap. And the minimap is basically just a different resolution of the same texture. We're not working with minmaps now, so you can just say it's 0. Then when you're loading, you load from this load location plus some offset. We don't need any offset, we're just loading directly from the particle's location, so it's another 0. Now, technically there's an alpha in there, so let's get rid of that by actually saying that this is a float 4, and this is part pose plus alpha, and then say float 3 part pose equals part pose plus alpha dot xyz. Just to be as explicit as possible here. Now that we fished out the position, we need to find the distance between that position and the world space location of whatever is being rendered on that pixel. So we need to first find a way to deal with world position. And world position is stored somewhere in here in the HLSL code specified by Unreal, but it's complicated and it keeps changing, so we're just going to drop it in through the node, world position, and we're going to create an extra input here and call this the pixel world pause, and drop that in there. So now we can find the distance between two float 3s, so let's just say that the brightness that we want to add is the distance between the part position and the pixel position. Except the distance keeps increasing as you keep going further, so this is going to blast wildly out of proportion. So instead we want to say 1 over the distance. That way we'll create this glowing orb that disappears as the distance increases. Now we can say, finally, the brightness is plus equal to the brightness to add. Now to test this out, we can just simply return the float 4 of the brightness 4 times. Semicolon. And make sure to say that the brightness to add is a float, because it can't figure that out. And now we're starting to see something. It's a little blurry though, so to increase the sharpness, let's square this factor of the distance. So 1 over the distance, let's just say times the distance. So copy that. And now we're starting to see something. And look at this object in the world. And there we have it. These glowing orbs are located around those particle positions in world space. And you can see, if I turn down the snapping here, you can sort of phase through those quantum orbs. Incidentally, these are perfect volumetric spheres. They'll never be pixelated or polygonal. That's another reason you might want to start doing pixel shaders in HLSL. Now let's zoom out here and see what else we can do with this. Now that we have this information of the distance, we're pretty much off to the races in terms of what we can do and how we can distort this object. For instance, let me see here, what's the tessellation look like on this? If I go from lit to wireframe, we can see that, okay, so this platform is quite low poly. Let me go back into lit mode. Let's really quickly just add some polys to this by going down here to the tessellation and just saying PN triangles and maybe crack free displacement. And just to make sure it can add some more, we'll add a tessellation parameter here, say something like 4, and plug that into the tessellation multiplier. And now instead of just changing the brightness here, let's just get a component out of here. Let's say the alpha, since we're not using that for anything else. And let's also make a float 3. Let's go ahead and plug 0 into x and y, and this alpha into z. So now we have a vector going upwards based on this brightness that we found. And now we're going to plug this into the world displacement. Maybe by a factor of, say, 100. And now instead of saying this is our emissive color, let's just get one component out of here. Well, let's just say we only take the red. And now we're going to linear interpolate. Clamp this, let's say 0 to 1, plug this into the emissive color, create 2 vector parameters, let's say one is red, one is green, Now, as you can see, we're getting this spiky effect going on here. However, since we're displacing so far from the original location, we're losing that. It's losing track of its original location, which is why we're not seeing the green. In this case, we can simply get around that by ignoring the z value. So we can do that by masking out the red and the green, which is the x and the y, and then appending 0, taking that in as the world position to use. That seems to have created an infinity somehow. Maybe take away the 100. This part here. Should always take care never to divide by 0. In this case, we can get around it by simply doing a clamp from 0 to 1. Actually, that won't fix anything. From 0.1 to 1 to say 100. There we go. Now you can see what I'm going for, which is those weird sort of colored lumps that you see in scanning tunneling microscopy. Maybe we can make this a bit more gradual by taking the square root. Now you might think there are other ways to do this, but we can take this even further. For instance, let's go back into the blueprint and let's create a timeline. Let's just call this Wobble Timeline. Let's open this up, say it's equal to 1 second, create a float that goes from 0 to 1 to 0. Select that, go 0.5, 1, 1, 0. View everything, select them, change it to auto. So now we can set a vector to move. For instance, let's create just a new random vector here. And set this equal to, we'll take this times 100. Split this apart and we'll put this in the X on its update. We'll also need to make sure to call this from the start, so let's add a sequence node here, which will do this path first. Then it will begin to play this timeline, which we will then have to set to loop. Now this should cause this to go back and forth, and we'll set this to be equal to that. So now this vector that we've made wobble will appear as one of our particles. Let's see if it works. When I play it, it doesn't work because we're only drawing to the render target once when on begin play. So let's go back into here and just simply change all of this. Alt-click to clear that and say that it runs on tick instead. Let's see if that works. There we go, and now you can see some sort of electron jumping back and forth. And as it overlaps one of the existing places, it spikes up even further. And you could do this as many times as you want. Like, let's say, let's make a few more. But in this one, we'll break the vector, and we will split this struct pin and split this struct pin. We'll take this wobbling X value, but we'll put it into the Y, and then we'll take this one and put it into the Z. Now you should be able to see all sorts of motion going on. We could go even further. We could say not just take these random particles, but to take, say, the player pawn. So for instance, I could right-click here and say get player pawn, and I could get actor location, connect that in, and now the player is one of the particles. So as I get closer, I might need to add some sort of factor here to increase the radius. So if I divide this distance squared by 25, now you can see there's a particle following me. And this would work with any number of players. It would work in an MMO. Now you might also be looking at that center spike. Why is there a spike in the center? Well, if you remember, I'm reading from 16 values, which means I'm reading across this entire top line, including all of these ones which are black. In other words, the ones whose location are 0, 0, 0. So instead of going over a fixed amount, say 16, let's also feed in the length of the array that we want to look over. So that's easy here. All we need to do is send the length of this array into the material. Now we haven't made any references to the actual material, so it would be tricky to manipulate this using a parameter. We could use a material parameter instance collection to do the trick, or we could just feed the length of the array into the array itself. So for instance, we could say get the length, and then we could set the array element of index 0, split this struct pin, and put the length directly into the x value. This first value won't be read anymore. Now we'll drop that into the logic. And now we can go back into this material here, go into our code. So now we can say int iterations equals the floor, to convert a float into an int, of loading the first thing's x value. So we can say load int3 0 0 0 0, and then we can take the x value of that. Now you'll loop while I is less than iterations. We'll also want to skip over that first index. Now hit play. And that should fix that spike in the middle. So what did we create here? Is something pushing up from the bottom, or is there some sort of green light source? Or is this a minimap representing the location of players or characters? It could be whatever you want it to be. Using arrays in Unreal shaders is something that most artists don't often find a need to do, so it tends to be one of those things that I find on the answer pages to be written off as something that's impossible. However, it's clearly not, and really this is just one of the ways in which to access arrays in the Unreal materials. Keep in mind that the Unreal materials are really just HLSL code at the end of the day, so anything available in HLSL is available in Unreal, which turns out to be pretty much anything you can imagine. I hope this tutorial gives you some idea or some inspirations for what you can create using modern real-time rendering applications and shader code. If it did, well, we've got plenty more inspiration to share here at Eigenverse.com, so be sure to check back often, and you'll find more exciting, wondrous, and mind-boggling things than you can possibly store in an array. Until next time, this has been the EigenTutorial, Unreal versus Impossible, and I look forward to seeing you in the next video.